Our Good Questions series is back tonight, and as always, it's your opportunity to get answers to things you've always wondered about.
What we're going to do in this video is quickly review exponential growth, and then use that as our platform to introduce ourselves to exponential decay.
And this week, we're talking about the Wisconsin Lottery. News 3's Mark Lovicott joins us with the winning question. This is something I've always wanted to know.
And it's really interesting what we found out. A lot of folks, people in our newsroom as well, I've played it before. They're lottery players. And you might know up until 2002, you could actually see the lottery drawing live on television.
It's a fun week, fun activities for people to have. For us here at the drawings, though, it's the same whether it's a 50 million or 500 million. Our security procedures are the same no matter what the level of the jackpot is. Muscle really knows that, because one of them asked, who sells the most, what location is selling?
Yes, yes, computer over there, don't you?
I didn't need a computer.
Yeah, we can always toss that computer.
Since that stopped, have you ever wondered who is responsible for drawing those winning numbers and exactly how it's done? One viewer was wondering, Kate from Madison wanted to know who pulls those winning lottery numbers and how do they do it? Good question.
So let's review exponential growth. Let's say we have something that, and I'll do this on a table here. Oops, let me make that straight. So let's say this is our x and this is our y. Now let's say when x is 0, y is equal to 3. And every time we increase x by 1, we double y. So y is going to go from 3 to 6. If x increases by 1 again, so we go to 2, then we're going to double y again. And so 6 times 2 is 12.
Oftentimes, lottery players have a very specific routine when they choose their numbers. At the Wisconsin Lottery, they're also very specific.
Hi, I'm Lori Minetti.
Gone are the days of TV drawings and ball machines. It now all happens inside this highly secure room, and only Jesse Waller has access to it. He's a pretty important guy.
Family don't actually get to play, but friends, then they would say, can you give me the winning numbers or something like that? But that's not going to happen because I have no control over that.
Square.
Good guess, but wrong.
All of our equipment is stored in a double-locked sealed vault, and it's alarmed. And just to get inside that vault, it takes a minimum of 3 people, auditors, muscle staff, and security people.
If 1 is 0, you once again, you keep multiplying by 2, and this will keep on happening. And you can describe this with an equation. You could say that y is equal to, and sometimes people might call this your y-intercept or your initial value, is equal to 3. Essentially, what happens when x equals 0 is equal to 3 times our common ratio. And our common ratio is, well, what are we multiplying by every time we increase x by 1? So 3 times our common ratio, 2 to the x to the x power. And you can verify that. Pick any of these.
Whoa, 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 whoa. See those numbers? Those are the numbers with my method. That first line. The computer gives you these for free. And
Cells.
These are what I chose.
When x is equal to 2, it's going to be 3 times 2 squared, which is 3 times 4, which is indeed equal to 12. And we can see that on a graph. So let me draw a quick graph right over here. So I'm having trouble drawing a straight line. All right. There we go. And let's see.
With the methods you're watching. The quantum method. What do we got there? 3? What's the date? October. Come on, focus in. 13th. Focus. Come on.
Weather.
13th. October 13th. Right? 3, 10, 13. Isn't that interesting? 13. October 13th. 3, 10, 23, 44, 47, 45. That's what was chosen with the methods you're watching.
Boat.
Always study your lottery methods backwards.
We have 4 machines that are just like the ones I have behind me, and 4 sets of balls for each color, red and white. And these are randomly selected just before each drawing, so no one ever knows, which piece of equipment is going to be used.
16, 24, 49. Play that each time, and eventually it will show up, along with your methods that I'm showing you. So watch this. October 13th, right? What came out on October 13th? Come on, focus. October 13th. 3, 10, 13. What do I got? 3, 10, 13. That's my method. Now I got the rest of these numbers wrong. As you can see.
We could go, and then they're going to be on a slightly different scale, my x and y axes. So this is x-axis, y-axis, and we go from -1 to 1 to 2. And so we're going all the way up to 12. So let's say that this is 3, 6.
Clear your head. All right. Tell me what you think it is.
Is it a star?
It is a star. Very good. That's great.
Everything in here is done randomly.
We're going to flip the blue and yellow coin to decide which random number generator to use.
You heard right. A computerized random number generator is used. No more ball machines.
In the machine itself is a little bit of an element called americium.
Okay. We saw that radioactive isotopes release radiation from the nucleus of their atoms. Remember that scientists cannot predict when a nucleus will decay, and that's because decay is a random process.
Which is radioactive, and it decays in a random fashion.
The result? Random numbers.
And I have the only key for this line.
The computers are very secure. They're standalone and not connected to any network. In the room, a witness from a private accounting firm keeps everything in check, and a Capitol police officer who actually presses the draw button. Everything is also recorded.
Self-test, draw numbers. The winning numbers are 5, 6,
6,
and 7.
In this video, we're looking at the idea of half-life, so let's get started. The half-life of a radioactive isotope is the time it takes for the number of nuclei of the isotope in a sample to halve. Now, that sounds a bit tricky, but the actual idea is quite straightforward. I'm showing you here a sample of a radioactive isotope. The white circles represent the nuclei, and when a nucleus decays, I'm going to show that by turning it red. So as you can see, the nuclei are decaying. Remember that this is a random process. Sometimes there's a relatively long period where no nucleus decays, and other times several nuclei will decay in a short period. So scientists cannot say when any individual nucleus will decay. Instead, scientists determine the time it takes for half the original nuclei to decay.
Which is radioactive, and it decays in a random fashion.
The result? Random numbers.
whoa, 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 whoa. See those numbers? You get to pick a set of numbers. Let's say you chose these numbers. 2, 6, 9, 10, 16, 24, 49. Play that each time, and eventually it will show up, along with your methods that I'm showing you. So watch this. October 13th, right? What came out on October 13th? Come on, focus. October 13th. 3, 10, 13. What do I got? 3, 10, 13.
And that's the half-life. Now, this isotope has a relatively long half-life. We can tell that because it's decaying relatively slowly. It will take a long time for the number of nuclei of the original isotope to halve. Here's a different radioactive isotope, and this one has a relatively short half-life. We can tell that because the nuclei are decaying at a faster rate. That means it won't take long for the number of nuclei of the original isotope to halve. Now, there is another definition for half-life, which I'm showing you here. The half-life is also the time it takes for the count rate, or the activity, from a sample containing the isotope to fall to half its initial level.
Random number generator is used. No more ball machines.
In the machine itself is a little bit of an element called americium, which is radioactive, and it decays in a random fashion.
The result? Random numbers.
Goose Island, Oregon, please. The number for Dr. Robert Hume.
7. The numbers come up instantly, but the process to get there is quite complex.
Okay. All right. Think hard. What is it? Circle. Close. But definitely wrong. Okay. All right. Ready?
Let's look at a still image. There's the neutron on the left, a sample neutron, which gets converted into a positively charged proton.
Random number generator is used. No more ball machines.
In the machine itself is a little bit of an element called americium.
Proton. It's got converted now, and therefore the particles coming out is an electron shown on the left hand side and one antineutrino on the right hand side. So the number of protons in the nucleus increases by 1.
What is it?
Figure 8.
Incredible. That's 5 for 5. You can't see these, can you?
No.
You're not cheating me, are you?
No, I swear, they're just coming to me.
Okay. Nervous?
Yes. I don't like this.
You only have 75 more to go. Okay? What's this one?
Out an electron as well as the anti-neutrino. The electron is negatively charged. The anti-neutrino does not have a charge. And the question is, why does the anti-neutrino come out? Well, that's a complex phenomenon of quantum number, lepton, which has to be maintained, and that's why two particles come out of that emission. As you saw in the animation, I wanted to remind once again that the electron which comes out as a beta particle is not one of those electrons which is orbiting the atom. The electron that comes out in a beta emission is created when the neutron becomes a proton.
Random number generator is used. No more ball machines.
In the machine itself is a little bit of an element called americium.
There's a couple of wavy lines.
Sorry, this isn't your lucky day.
I know. I'm getting a little tired of this.
You volunteered, didn't you? We're paying you, aren't we?
Yeah, but I didn't know you were going to be giving me electric shocks. What are you trying to prove here anyway?
I'm studying the effect of negative reinforcement on ESP ability.
The effect? I'll tell you what the effect is. It's pissing me off.
Well, then maybe my theory is correct.
You can keep the $5. I've had it.
I will, mister.
I'm getting a little tired of this.
You volunteered, didn't you?